So we are talking about this gearbox modeling using Simerics-MP+. This is the second webinar in our series in 2024. I would like to thank my co-host, Dr. Raghuvanshi Godavarthi, for joining me today to help me with this demonstration, and also Dikshit Bonukasu, who's behind the scenes doing all the heavy lifting and making this happen. So let me just see if I can put this window aside. Okay, so let's get started. So before we start, we just want to make sure that if you have any questions, you can post it in the chat window. We will address them towards the end of the webinar. Our contacts are here. My contact email is cs@simerics.com. Raghu's is rvg@simerics.com. You can also call us if you have any questions. And you can contact me later if you have further discussions to be had with this topic. In terms of the demo, or in terms of the outline, we're going to just talk about Simerics, our gear meshing capability, then talk about a demo case that Raghu is going to show, and some of the benefits that we are seeing with using this model to study a gearbox, and some results that come out of the demo, and some announcement about the upcoming webinar and any questions or answers that we want to talk in. So first, about Simerics. So we are a CAE company. Our headquarters is in Bellevue. It's in Washington State, a suburb of Seattle. Our office here in the application support wing is in Detroit. So it's a Novi, the suburb of Detroit called Novi. And we have an office in Germany, in Rothenburg, and also in India, in Bangalore. Essentially, who we are engineers and researchers who want to produce path-paving innovative technologies in the world of CAE. So in this venture, we are trying to kind of come up with a tool so far in terms of CFD tool, which is very robust, accurate, fast, and automated in terms of doing any virtual analysis and design. I think the infancy, we kind of started with the software being called pumplings. That's because any application which requires like moving machinery. So as you guys understand, it's going to involve like squeezing, expansion, or squeezing into gaps that are very micron sized, and doing this in a package that is fast, robust, and accurate is something that is of a big challenge in CFD. And that's the starting point of Simerics. So we kind of started the toughest problem that's possible. And we're kind of working our way backwards in some sense, because we know that that market is tough and we are able to kind of capture that. And in terms of doing moving mesh, I think as is a proof that we have done quite a lot of different types of pumps, and we have published those. Modeling leakages and micron size gaps accurately is also a big challenge. And in terms of how we do those, let's say in terms of how we make the software fast is, one way is the automated way of meshing it. So we have this proprietary binary grid algorithm, which automates the meshing process. Automating meshing is good, but sometimes what happens is, even when you kind of have sometimes cells that are not perfectly good in terms of aspect ratios, we can still run the simulation with robustness and come up with a quick turnaround. So that is, I think, the beauty of how we do the simulations. And we can, let's say do the mesh of a pump quite well, but I think it should be easy for the user to do it as well. So then our thought process was to create a template-driven workflow. So this will kind of automate majority of the steps that is required to set up a model, so it's easy to use. So we have templates for various types of pumps, compressors, vehicles, etc. And this kind of shortens the learning curve for the user. So that is our motivation behind providing templates to make it easy for the user to set up a model. And also it eliminates high-end dependency on development or manpower in terms of what you guys need to put into setting up a model. So the tagline is robust and fast and accurate. VOF through tiny clearances, cavitation, micron size gaps. These are typically challenging problems in terms of converging and also conserving mass. And we can do this multiple times faster than other commercial codes. And this has been validated across several different industry applications, verticals, right? And in terms of the software suite, we have this CFD market that we have, in terms of the physics, we can do multi-phase flow with volume of fluid cavitation. We can do heat transfer, we can do turbulence. We are just coming up with an FEA tool that's going to be released shortly. The goal is to kind of couple FEA and CFD together in problems that require the tight coupling. And we also have written our own optimizer from scratch based on the Bayesian algorithm. And this has now been rolled out in the last few months. And we have done quite a lot of cases with our beta test version as well. And this works well with our CFD workflow. Excuse me. Also, we have been partnering with different OEM products. This is to kind of try to understand and look at the design market as well. And so we have partnership with Orca 3D, with PTC Creo Flow analysis, with SolidWorks, with CF Turbo, with cases, with GT, with Autodesk Fusion, and with Rhino, with Simscale, the Simerics-MP on the cloud, and with NX. So what this offers is, if you can launch that product, you can probably access Simerics solver inside that product. So that's the partnership that we have here. Just to kind of give you an array of different types of pump templates that we have. So you can see all the different types of pump templates and valve templates. And on top, we have also developed templates for the compressor industry and the automotive field. So the general gear template is the one we will be focusing on today. We also have templates for vehicle front-end airflow, underhood thermal, water weighting, tank sloshing, piston cooling. And in the marine, we also have templates for the hull and propeller. So let's talk about this intermeshing capability. I think one thing to start off right off the bat is the accuracy. I think we can see for different sets of gear pairs that we have done for gearboxes. So first was the FZG gear. Then we have a couple of cases from the Ohio State University Gear Lab. So we have run with the same set of best practices. We have run multiple of these gear cases, and we are getting quite a good correlation with the testing data. This is the power loss essentially normalized with respect to the rotational speed. And you can see for 3 different cases for different RPMs, we are able to kind of get a quite good correlation with testing data. In terms of the automation of the workflow, as I briefly mentioned previously, we also have this done for the gear meshing. So we have this general gear template. So the general gear template offers this advantages that we can handle any number of gears. We can do both internal and external gears. It will capture the intermeshing automatically for the micron size clearance. We don't need to scale the geometry. We don't need to cut the teeth of the gears. We don't need to move the centers apart. So we just capture the clearance as such. We just need a small amount of clearance. It could be in the order of 10 microns between the gears. This is a cross-sectional view that shows like a planetary gear system, and you can see the small mesh between the different gaps. We also have special templates that handle special applications like the planetary system. So it makes it a little bit easier for the user to not really write code to make the movement possible. For the helical gears, we can also detect automatically the helix angle. So this is you just need to read the CAD and it'll automatically populate the angles. We also have the custom stored defaults. So this will help kind of automate the mesh sizes for a particular application. So let's say if you have a gearbox, you have frozen the set of best practices that you need in terms of mesh size. We can just put that as default, and we can just customize it so that you don't need to keep redoing this best practice every single time. And we also capture this gap quite accurately. We can have 10 to 12 cells in that small clearance of 10 microns. So each cell can be out of a few microns or less than a micron, and still the simulation can run quite robustly. So in terms of the robust simulation handling, I think I show a panoramic view of what we can do in terms of this simulation. I'll talk about this case a little bit more in detail later, but what you're looking at is like a transmission system, and we are kind of filling the system and trying to understand the lubrication of it. And so multiple levels of challenges here. One is you have tiny clearances. And in those tiny clearances, you have like a few micron cells, right? And on top, you have to run a multi-phase VOF with the interface being captured sharply so that you can understand the lubrication accurately. So, and you have to do this within a reasonable amount of time so that it doesn't take a long time to run this model. So I think this is the full variety of complexities that we are showing that we can handle. In terms of the simulation time, I just want to hit upon the point that this is like a gearbox with an electric motor. So you have the drive unit on the left side and then the electric motor, which is getting cooled. So for a model this size, typically, the mesh size is in the order of 60 million, 70 million. That's what you're looking at. And we also have prism meshes that will kind of we can kind of ensure that we capture the oil film on those surfaces accurately. That is to ensure that we have correct cooling or the heat removal from the solid. In terms of CAD preparation for such a complex model, since we automate the gear mesh quite easily, and then the rest of it is a bulk mesh, which is again our automatic binary structure. It's quite easy to prepare this CAD. I would say it takes from CAD to CFD model, even for a very dirty CAD. Some of our guys can do it within a day. And the runtime is in the order of like 3 to 4 days. It's using 720 cores. So it's quite a quick turnaround for a model of this size. In terms of capturing all intricate solid movements, that's one thing that because of the intermeshing can help us do. So for example, we are showing an animation of the planetary gear system where it has the gearbox on inside of it. You have these needle bearings. So we're looking at the lubrication of this entire system. We can capture these clearances right for both the gears as well as the bearings. So in essence, we can try to, if you're looking at lubrication or a power loss, we have less assumptions taken into modeling this type of system. So that is something that, and also in terms of the velocity field, you can see we kind of color this bearings with the velocity contour, and you can see the distribution of the velocity being accurately captured here. To top it all, we have unlimited user support. We have a talented team of postgraduate trained application support engineers. We have had more than 20 plus publications in the last couple of years. So our support is not just to resolve issues. We do that, but I think we kind of take pride in forging simulation pathways for your team so that you can get back to your customers on time with confidence in your results. So that is something that we uniquely do as a CFD company. So now I'll stop sharing. I'll let Raghu take it up and show us.
I hope we all can see my screen now. Yeah. So I'll quickly demonstrate a setting up of a planetary gearbox. Before I do that, I would like to demonstrate on how we can set up any 2-gear model or any gear model, create a gear mesh using general gear template. So that's here we have 2-gear model that I bring in. So we need the prerequisites required for setting up a gear model is basically we just need to bring in the solid gears, okay, and create a cylindrical and bring in cylindrical surfaces that represent the shroud of the gear surfaces. So in this case, I brought in the small gears, cylindrical surfaces, so both the big gear and the small gear surfaces. Now we just start splitting up the surfaces that are required for the template. So I'll just split by angle the gear surfaces. And then just split disconnected. Yeah, so now we just need only the outer gear surface for the for meshing using the template, and then we split out the cylindrical surfaces. Yeah, these are the cylindrical surfaces, so we only need the outer surface of the cylindrical surfaces. Just split by angle. So we don't need the rest of the surfaces, so I can just delete them. I'll just now I use with the general gear template, we can just mesh the gear mesh using the general gear template. So under the rotate template meshes, we have different customized templates for different applications. So this general gear is one such application. So wherein we can just generate the mesh for any gear set. So here I'm talking about the gear set, which are spark gears, but we can extend it to helical gears as well, as Chirag mentioned in the slides. So I'll specify the rotational axle direction. So we just add the gears. So this is an external gear. So first is the big gear. I'll just name it as a big gear. The gear center in this case is, so I'll just specify the big gear center. And then the gear surfaces. So I'll assign the big gear surface and then the outer gear surface for the bigger gear. So automatically you will see that the number of teeth gets populated. Okay, so as soon as we add the gear surface, the number of teeth gets detected, and then we can specify the prism layer thickness. So in this case, let me choose a prism layer of 20 microns, and we can specify the number of layers in that prism layer, as many as we want. So here I'm just leaving it to number 3, and this is our reference gear. Okay. And I'm just choosing the mesh type. We can choose the mesh size, whether be it medium, coarse, fine, or we can specify the users. We can also specify a different set of mesh settings. And then I add the smaller gear now. So I just assign a small gear. So select the small gear, assign this gear surface. So, and then I just specify the cell center. And then specify the outer surface. Similarly, I specify the prism layer thickness here and the number of layers. So with this we can just generate the gear mesh. So as you can see that quickly it has generated the gear mesh. So, and you can see the mesh on the gears. So there's a gear mesh and it captures the intermeshing between the gear teeth that you see here. And it can capture the clearances between the teeth as well. So it can go up till any number of microns between the gear teeth. So with the general gear meshing, it automatically creates a general gear module wherein we can specify the operating conditions. So here I will choose the big gear as my main gear, okay, and specify the direction of rotation, the counterclockwise speed as like 1000 RPM. So automatically the speed ratio is set for the big gear as well as the small gears. So small gear, the speed ratio would be 1.55, and specify the number of time steps per revolution. So I'll just quickly start the simulation. So you can see the gears rotating with the, you can see the gears rotating and capturing with the, even you can see the mesh motion happening between the gear teeth as well. So this is how you can quickly set up a gear mesh using the general gear template, and it can be extended to any number of gears, which I will show it in the setting up of a planetary gear set. I'll just stop this case now. And so coming to the setting of the problem statement that we are looking at. So this is the planetary gear set that I'm going to set up and simulate in this demonstration now. So there's a planetary gear set which has a sun gear and 3 planet gears and the ring gear. So the sun gear is rotating at 600 RPM and the ring gear is stationary in this case. And this is the housing of the complete planetary gear set. So it also has a carrier at the back, which I'll show you in the geometry now. So this is the geometry that we have imported as STL. So we import the carrier volume, which is the rotating volume of the carrier, and the cavity volumes around the planet gears. Okay, and in the planet gear, the ring gear, and the sun gear, along with its cylindrical surfaces. Okay, that are required for meshing using the template. And this is the housing of the complete planetary gear set. So next we just now start splitting up the gear surfaces like I've shown in the previous 2 gear model. So we just need to split up the gear surface, outer gear surface, and cylindrical surfaces. So I'll just during the demonstration I'll just avoid splitting up because of the time constraint. So I'll show you the model where we already have the split. Okay, so these are the carrier surfaces. So where we split up the we split up the surfaces which are connecting which are the interfaces between the carrier volume and the housing volume. Similarly, we have all the splits for the cavity surfaces which connect with planet volumes, sun gear volume, and the ring gear volumes, as well as the housing from the top and front. And then we have the housing surfaces that we split up to connect with different volumes. This is the housing outer surface, and these are the planet surface. This is a planet gear with the planet outer gear surface. There's a ring gear with the ring gear surface. It's an internal gear here. And then the sun gear is sun gear surface. And for the template, you will notice that they showed there are 3 planets here, but we just need to bring in 1 planet for reference, and we can set up the complete planetary gear set and specifying the number of planets. So these are the splits that needs to be performed. And once we perform the splits, and then I'll start setting up the mesh using the planetary gear set template. So planetary gear template is an extension of the general gear template, which is specifically for planetary gear set, so that it takes care of all the motions and complicated motions like the sun gear rotating as well as the planets rotating around their own axis as well as revolving around the sun gear. So that to take care of this motion, so we have a extension of the general gear, which is the planetary gear set template. So here I just start setting up using the planetary gear set template. So this is the rotational axis as the Z axis. So we can specify the mesh size. I'll just choose it to be coarse right now. And then we can control. So here you can see that actually the planet gears, the ring gear as well as sun gear, we brought in as a spark gears, but we can convert them to helical gears as well, or directly bring in the helical gears. So I'll just specify as helical gears to yes. And this has a sun gear. This has a sun ring gear. So we set to yes. Gear set center, in this case, it's at the origin. So I'll leave it to 0, 0, 0. And the sun gear options, I'll just add the sun gear now. And the sun gear outer surface. So it automatically detects the number of teeth and specify the helix angle of the, this I specify the total rotation angle for the sun gear. And so now I assign the planet gear surfaces, which is this is the planet gear surface or gear surface, and then the outer surface, and specify the center of the planet gear that we have imported. Number of teeth already automatically detected, then specify the total rotation angle, which is like 26 degrees. And number of planet gears in this case is 3. So then we assign the ring gear options, ring cylinder, and then specify the total rotation angle. So after this, we can even control, we can have more advanced options in terms of specifying the number of viscous layers here. So in this case, we can, I'll just mention as 10 microns and number of layers to 2. Okay. And then they just build the planetary gear set. So it takes like less than a minute for it to build the planetary gear set. So as you can see, it's pretty, very straightforward, and it's very much customized for setting up a planetary gear set where we can choose the sun gear, planet gears, ring gears, and specify the number of planet gears as we want, as many as we want, and bring in just only the reference planet gear surface. I'm sorry, I think I missed. Yeah, just. Sorry for the typo. So it takes like, less than a minute to set up the planetary gear set mesh. So this, as I said, we can just bring in the helical gears directly, or even specify the rotational angle to convert the spark gears into a helical gears. Just wait for half a minute. So after we set up the planet gear set, we use the general gear mesh to set up the other volumes, and then we connect the interfaces. So now you can see it has generated the mesh for all the planets as the ring gear and the sun gear. We can show you the grid on it as well. So, and it also have the viscous layers on the gears, prism layers on the gear surfaces. Okay, so I'll just switch on the now. And now I assign, create the mesh for other volumes. This is the cavity volume. Using the general measure, we create the mesh for the cavity volume. I'll just keep this as a single volume mesh. Save as cavity and create the mesh for the cavity using the default settings. So we can control the mesh settings as well here. So the cavity surface, cavity mesh has been generated now. So similarly, we say generate for the carrier volumes using the general measure. I'm just keeping it to the default settings right now. And then for the housing. So now we have the mesh for all the volumes. In like less than 5 minutes, you can see that we have the mesh for all the volumes. So let me take a cross section to show you the cross sectional mesh. So have the mesh cross section you can see, and we can control the mesh in different volumes as well. Just make it a Z plane. So there's a mesh across the case as well as the cavity volumes and the outer housing volumes. Okay. So now we connect the interfaces between the volumes. So that's the next part of the setup. So I'll just start with cavity volumes. So this cavity surfaces will be connected to the planetary gear outside surface. And similarly, for the other planet gear, we create the interface. So you will see that under the interfaces, it will get listed under the interfaces, the interfaces that we are creating. And then we create for the other planet gear as well. So it has now created interfaces between the planets. Then we have the connection, we have the interface between the cavities and the ring gear outside. So we just select those surfaces and create an interface. And then we have with the sun gear outside as well, sun gear and the cavity. So this is another interface. So this now we have connected the cavity radial surfaces with the different volumes. Okay. And then we have the cavity bottom surface, all the bottom surfaces that corresponding to the cavity and the planet gears, the ring gear and the sun gear, they connect with the housing bottom surface, so that we have which we have specified as cavity bottom. So we connect this as an interface. So then we connect all the top surfaces, top side, so the planet surfaces, the ring, sun gear, and the housing. And then we connect the carrier surfaces with the housing. And then carrier radial surface with the housing radial surface. And the housing top surface with the carrier top surface. So now we have created all the interfaces between the volumes. So if I look at the interfaces list, you will see all the interfaces connecting different volumes between the gears and with the housing as well. So all the interfaces are connected now. So the next step in the workflow is after meshing, it will be assigning the physics and conditions. So as I said, with the planetary gear set meshing, we automatically the planetary gear set module is added where we specify the operating conditions. Then we add the physics. So here it is a lubrication phenomena where we solve using the multi-phase flow physics, multi-phase. We add the multi-phase and turbulence. We add this physics. So and then we specify under the multi-phase, we specify the fluids, oil, air, and we can choose the numerics as well. So these are the best practices that we follow typically. Under the flow, so there is a gravity in y direction, negative y direction. So we specify the gravity force here, which is under negative y direction. And under the planetary gear set, we specify the operating conditions in terms of like angular root definitions and the time definitions. So we choose number of time steps per tooth as like 10 time steps per tooth. And we can specify the number of revolutions, like how many revolutions we want to run the simulation. And the primary input is sun gear. Based on sun gear, we define the time steps. So here the sun gear is rotating counterclockwise and rotational speed is like 600 RPM. And secondary input, we can choose either planet carrier as well as the ring gear. So in this case, we know that ring gear is stationary. So we just assign as ring gear, and automatically the speeds of the carrier as well as the planets will be calculated based on the wheels equations. Okay, so these are the operating conditions that we specify. Once we specify the operating conditions, so we go into the boundary conditions for all the rotating surfaces. So the carrier will be rotating. So all the carrier surfaces will be assigned as a following planetary gear. So we can choose we can assign the boundary conditions corresponding to either being it following a sun gear, planet carrier. So these are the surfaces that we assign automatically once we assign the boundary conditions as that it will be a rotating wall boundary conditions with the speeds corresponding to either being the sun gear, the ring gear or the carriers. So in this case, the carriers, you can see the speed is being already calculated based on the Will's equations. And similarly, we assign the surfaces, the cavity surfaces, even these cavity surfaces follow the planet carrier. So these are corresponding onto the planet. So they also follow the planet carrier. So we assign them as planet carriers. Then corresponding to the housing. So we have housing corresponding to the carrier. These also again follow the planet carrier. So we assign them as following the planet carrier. And the cavity bottom surfaces, they are actually on the connecting to the gears on the top and bottom side of the gear. So we assign them as a gear axial velocity, gear axial wall. So that based on the radial coordinate, the velocities are specified. So automatically the velocities would be specified. And now other planet gears, all the planet gears that we have, so automatically the planet gears are assigned. You can see the planet gears are assigned. And we can choose we choose all the planet gears, all the gears, and we choose the outputs to look at, like we need the phase area fraction, the weighting area. To know the weighting area, we switch on the phase area fractions, and also the power that is required to calculate the churning losses. So even the power output is automatically switched on all these gear rotating surfaces. So once we have the boundary condition set up, so we assign the volume properties. So then we choose the fluid properties. Here density is 800 and air is solved as ideal gas, and specifying the viscosity of the oil 0.0029 and switching on the surface tension with surface tension value of 0.04. So these are the volume conditions, and then we need to initialize the oil as I shown to a level of like 0.03 meters. So we initialize the oil using the expressions. So I'll just copy the expressions right now. So it's pretty simple to write an expression here. So here the fraction F oil corresponds to fraction of oil. So below the Y level of height 0.03 meters, all the cells will be initialized with oil, and above 0.03 meters, oil cells will be initialized with air. So we choose F oil and F air as our variables. So selecting all the volumes, I initialize the oil and air. So here it will be F oil and F air. So now we initialize with oil and air as well. So I'll just save it. So with this, we are done with the setup, and when all the conditions have been set up, so we can just proceed with the simulation. So I'll just show you quickly and the initialization of oil that we have using the isosurface. So we specify the volume fraction of oil about 0.5. You can see that it has been initialized in the negative Y direction up to a level of 0.03 meters. So this is the initialization level. Now we just go into the simulation tab. We can assign the number of iterations to like 10 per time step and change the result saving frequency based on the interest that we have, and start the simulation. So I think as the simulation is progressing, I think I'll hand over to Chirant, and he will continue the presentation. Before that, I just so here is the mesh motion that you can see how the sun gear rotation and the planet gears rotate along with the sun gear and based on the carrier and along with the carriers. So this is how the mesh motion that we can that is handled by the Planetary Gear Set template. I think I'll over to Chirant now. So once it starts running, so I'll show the results after some time after Chirant finishes.
Thank you, Raghu. Yeah, let me share my screen. As Raghu said, you have some fluid extraction, but in terms of just to summarize the steps of the model setup, in terms of the gear mesh, the good part is you just bring in the solid and you can just directly set up the mesh. And then the fluid is the rest of the casing fluid is all you need to extract. Then you mesh it, interfaces you create, and then populate the physics, the conditions, and the boundary and the volume conditions, and you can start running it. So let's look at some engineering benefits. So I think the most prevalent question is to us essentially is why do we need to intermesh? So we kind of understand to do kind of a thought experiment on what physics that we get while we intermesh compared to when we just do an overlap approach. So in the left, we have this intermeshing approach that we just demonstrated. So we can capture the actual T to T gap in the order of microns, right? And this also kind of captures the squeezing and the shearing of oil between the gears. And the power loss can be affected. The prediction of that can be affected by this physics essentially. Whereas in the overlap approach, we are not doing the intermeshing. So first of all, the oil flow between the two gears, the flow going to one side or the other side is not going to be captured. It's either going to go with this gear or the other gear. And of course, then there is no squeezing or the shearing of the oil. So the power loss prediction might not be reasonable. So what we did was kind of cook up a simple gearbox that we can show in a demonstration. We have some fixed level of oil. And of course, like there is in this section, it's not visible, but the oil can seep its way into this gear location. So initially, the oil gets thrown, and it'll come back and then keep getting thrown. It becomes a quasi-stable behavior. So two things to notice here is one is when the oil goes to this intermeshing zone, there is resistance thrown by these gears for the passage of oil, basically. So it won't let the oil freely flow through that gap. So you will notice that the splashback of oil because of this resistance is more severe in the case of the intermeshing compared to the case where you have the overlap. You can see kind of it whistles out or fizzles out here, the splashback. The reason is on the other side, you can see the oil kind of gets thrown to the left top corner in the overlap approach because there is no resistance between the gears. Whereas in this case, the amount of oil that is getting thrown to the left top corner is lesser. So that is two differences that we notice off the bat. The other thing is kind of zooming into the space. You can see some type of pressurization that happens. Here you can see more oil that kind of makes its way inside. So the pressurization can be seen a little bit more clearly here. So if you plot the pressure gauge between say 0.8 and 1.2 bar, the pressure range, and you can notice that there are regions here where the pressure goes and becomes like magenta or red color, which is in the order of 1.2, 1.3 bar. But here you can see that it's all like in the range of atmospheric pressure. So there's no pressurization that happens. That's because there is no squeezing of the oil or the air there, or there is no shearing of oil there that is happening in the case of the overlap approach. Also, if you look at monitoring the power loss or the windage, or you can call it the drag loss on the gears, you can see that the intermeshing in a normalized sense will predict probably like 2 or 3 times larger power loss compared to the overlap approach. That's because, for example, this case, it's probably a little bit larger. We have seen that more realistic cases, it could be in the order of 2 times larger or 100% difference. That's because you're having this pressure effects as well as due to this resistance, you will have more oil hitting the two gears, which causes pronounced spin loss, basically. So this is one kind of study that we did that we wanted to show. So then having established that the intermeshing is the more accurate way, we kind of then looked at a couple of papers in the literature. One is this FCG gear that's been tested and some data is there in the literature, and also the other one is the poly gear that is tested in the Ohio State Laboratory, and some test data is there in the literature. So first look at this FCG gear. We look at some qualitative results of how the distribution of oil looks like in the case of the test compared to the case of the simulation. So two things of note here. One is as you increase the speed, you will see that you'll probably kind of fling a little bit more oil. So you have little more this oil, let's say oil jet or oil stream that gets captured on the gear tooth. And the other thing is the side splash. So due to this oil churning, I think the bigger gear especially kind of pushes oil towards the side because the container being small. You can see some in the lower speed, you get some oil rise up in the corner. As you go higher and higher speed, you see the oil rise up in the corner being larger. And that is something that I think the simulation can pick up quite well. So qualitatively, the results look quite encouraging. And then if you go to the quantitative numbers, these are run at lower speeds, but at higher speeds, the window gets really, polluted. You cannot see much of the clear interface like you see here. So they don't have videos, but they have quantitative numbers. So that's what we try to compare against the churning loss with 2 different temperatures and 3 different rotational speeds. So the rotational speeds are 1400, 2700, and 5200 RPM. That corresponds, the highest RPM corresponds to 20 meter per second tip velocity. So if you look at the test data, and then the current work is the red bar diagram, and then the previous work that has been done is there in the literature is the green one by some other commercial code, and then the SPH code is the purple one. I think what we notice is consistently we can kind of be closer to the testing data with the same set of best practices that we put together in terms of mesh size, time step, and the VOF settings. So that gives us good confidence that that we are kind of capturing the physics appropriately in terms of this modeling. We did few more cases. The second one I can show here because it's the public is the polygear spin loss. So we have a ring gear, the dimensions of it shown here, and a pinion gear. And we kind of mesh this as we see here. This is the best practice. We have to have refinement zones to kind of address the oil that is splashing around. And this is the results, how it's look like for 1500 RPM. We have an isosurface view of 0.5 volume fraction of oil and a cut section view showing the oil in a cut section splashing around. So what we notice is there is a level of oil that is in the beginning. It gets kind of disturbed and the level drops because some amount of oil goes into transit. But that oil makes its way back and it becomes kind of quasi-stable. If you look at this pitot tube, if you run it for a while, the pitot tube becomes quite static, like it'll kind of just keep oscillating about this space. And then you will notice that there is like a quasi steady state behavior where a fixed amount of oil keeps like rotating in the system basically. And that is also kind of shown in this power loss. So if you kind of look at the curve for the power loss for the 3 different speeds, you will see that instantaneously there is a disruption in the power loss because the large amount of oil gets scooped by the gear, but then it kind of reaches like a balance and stays pretty much kind of stable over multiple revolutions after a certain amount of time. And this is run for, let's say, 2 seconds, and we can see that's 30, 40 revolutions, and it's pretty much stable basically. And in terms of the experimental comparison, again, we can show here that we are capturing the trend as well as the numbers quite reasonably well in terms of the churning loss. So we can see the experimental data in blue and the the Simerics data in the orange. So I think we are running a little bit short on time, but I'll kind of quickly push through this one. This is the transmission system. I showed a couple of animations in the previous slide. So this is a paper that we published along with General Motors in the current SAE that just went by this year. So the goal of this simulation is to understand lubrication of multiple bearings. Actually, this system has 1, 2, 3 ball bearings, 1 thrust bearing. There's a thrust bearing here. So that is 4. And then we have 2 sets of needle bearing on each of the planet gear, and there are 4 planet gears. So that's a total of 8 needle bearings. So 8 plus 9 plus 10, 11. So totally 12 sets of bearings. And then we have the gear mesh as well, which is like 4 gears, planets, 1 sun, 5 gears, and then a ring gear, totally 6 gears. And I think for meshing, we have specialized meshes sometimes to kind of address some of these leakage gaps. We call it the structured mesh. We can morph it to very complex shapes. For example, here we have this small clearances. We kind of morph the structured mesh to fit like 6-7 cells into this 200 micron clearance. And I show a couple of these other sections where I show the nice mesh that we create here. This is the general gear template, the planetary gear system mesh that Raghu just described. So this is a 4-planet gear system. So we mesh this with the details as well. And then we have the ball bearing, section of the ball bearing here. And then this is the panoramic view, or let's say the overall view of the system after we mesh it. So the inlet and then we have multiple outlets at 3 different locations, and we are looking at the lubrication of oil. The goal is to study the needle bearing. So we have 2 designs. It's detailed more in the paper. So one design where you don't have like oil going, there is no oil passage to the needle bearing, but in the second design, they have an oil passage to the needle bearing. So we want to see how much oil gets funneled through this passage into the needle bearing. So that's the goal of the study. It's kind of showing an animation of what goes on here is something that we saw before. Just to end it, we kind of show that we can look at the different amount of oil getting captured in the bearing. So in the new design where you have this channels, we get more wetting, like it's 20% now compared to 10% before. And in terms of the gears, we don't see a whole lot of change in the gear wetting. There is some change in that. So some amount of oil gets reduced in the gear, which goes to the bearing. Whereas in the old design, there's more amount of oil in the gears compared to the bearing. So I think what this study shows is the value of doing something more accurately in terms of the confidence you can get in the simulation results, right? So if you can capture most of the, let's say, physics in terms of, reducing I think CFD itself has a lot of assumptions in there, but as much as assumptions can you reduce to get to a realistic estimation which you can have confidence in, so that you can have some hope in redesigning or reworking your design, right? So that's what we want to get to, and that's the goal that we are fighting to hit. So now I'll stop. I'll give it back to Raghu, and he can probably show just quickly some post-processing before we run out of time.
Yeah, sure, Chan. Just a minute. So yeah, I hope you can see my screen. So now the simulation that we have started, you can see that it has run like 22 time steps, which is like 2 pockets of sun gear. So it has, like we have mentioned, 10 time steps per tooth that we have mentioned. So it has run like 20 time steps in like 10 minutes. So you can, the complete revolution, it takes like less than 3 hours for this on a workstation that I'm talking here, 20 with 24 cores. So I'm just showing here the velocities that already automatically the template assigns. So you can see that on the gear surfaces, based on the radial locations, as well as based on the rotational speeds, it assigns the surfaces. If you look at the planet case, the gear surface that is touching towards the sun gear will have the higher velocities, and towards the ring gear it comes up, the velocities die down because the ring gear is stationary. So that's all these are taken care automatically by the template. So now I'll just show the results that already we have simulated. So in terms of results, you can look at the oil isosurface, look at the distribution. So you can see that oil getting splashed around because of the rotation of the gears into different parts of the housing. So the gear is rotating counterclockwise. So you can see the oil getting splashed onto the housing as in different parts of the gears. And we can look at the wetting fraction of the gears by plotting the phase area fraction that I'm showing here. So all the gear surfaces, they are kind of wet by around 20%. You can see them wetting by 20%, and almost they get stabilized in like 3 to 4 revolutions. And we can look at the power on each the gears as well as the total power. So this is the power on each of the gear surfaces, and then this is the so this is the total. This is the summation of the total power on all the gear surfaces. So we can predict the churning losses. So it's like 2.4 watts in this case, so that we specify, and we can look at all the wetting fraction of all the gears. So these are some of the outputs that we can look at, and even create some animations in terms of looking at the wetting area of the gears. This is how the oil film is forming on the gear surfaces. So towards the bottom, since they are dipped in oil, so you'll see the complete oil, gear being wet, and towards the top you'll see spots of black, which means that it's not completely wet as it moves towards the top side. So these are a few of the animations that we can create and look in intricately in terms of getting more insights how the oil distribution is happening. So these are a few of the post-processing that one can look at in terms of simulations and predict the power losses as Chinant was showing in his slides. Maybe now we'll take the questions. I think, Chirant.
Yeah, I think, yeah, so we can now, I'll share my screen back, go to the questions. Okay, so just want to quickly say that the next webinar, we tentatively scheduled it on November 13. We are thinking about talking about the full vehicle under hood thermal simulations using Simerics-MP+. So now we go to the questions. Let me do it one at a time. We go to the WebEx. Let me stop sharing first so that I can see the questions. First question is from Nawab. How does Simerics able to model flow through real small clearance? Other CFD suffers from robustness modeling that any special treatment. So I think we have put a lot of focus on our solver. I think it's something that we wanted to kind of build inside out in terms of the code. The solver keeps our attention, let's say, to 90%. Other things we need to improve as well, but I think the way it's been written from scratch, as well as it combined with our measure, I think offers the special ability to kind of keep the solution without suffering robustness, so suffering from like instability or diverging. So I think a lot of tricks to the trade. Not a lot I can divulge other than that, but I would say that's what I would say here. Charlie's second question is, does Simerics handle hypoid queries? I think this is something that we just have a test version out. We should be able to do this, I think probably beginning of next year. Right now we don't have the capability. Next question from Nawab. For this 2-gear case you're showing, what if width of one gear is bigger than the other one? Can the general mesh template be used, or they need to have same width for the structural mesh generation? Yeah, I think this is a good question. Let me quickly share my screen. Yeah, for example, if you can see my screen. So if you have, let's say, a planet, I'll just take this example of the planet system that Raghu just showed. So let's say here we have the same gear width in terms of the depth of the gear, right? And so if I go to measure, I just generate the mesh, and you can see that it's nice structured mesh and it cuts the mesh correctly. We can kind of do this where, for example, I'll just translate this. So now this gear is kind of sticking out. So the sun and the planet have some offset. We can use the same mesh settings that we have generated. So it's in build mesh, and you just click the button. And what the general gear does is it'll automatically bifurcate the mesh. So for example, the common region between the two is this region. So it kind of has the intermeshing zone there. The other zone you can see, which is not common, it kind of creates a mesh automatically, also for the sun and the planet, and it'll do it automatically. We don't need to have any special treatment for it. You will just see that it'll have 4 domains because there is a common intermeshing zone now, plus an extra zone for the planet and an extra zone for the sun, basically. So, and this can be any which way. It's not limited to one direction. It can be quite extreme, and it'll still kind of do it. So it's not it's quite robust in terms of how the measure deals. For example, it could be like this, and you can mesh it, and you can see it kind of meshes it with the intermeshing zone correctly captured. Okay, so that's the answer to that question. For the next question, Ding Hao, how much clearance in terms of micron is recommended for the gear contact region when setting up the CAD? So I think we need some clearance. So I would say in the order of 10 micron is sufficient. We can even go smaller than that if it's necessary to do it. So I think we need to have at least few micron clearance, or else you will have overlapping mesh issue basically. So that is something that user needs to make sure that the CAD has some tiny sliver of clearance to begin with. Next question from Shanmugh. What would be the advantage of using a Simerics plugin in a CAD software over the default CAD import option? I think this has got to do with nomenclature. For example, let's say you establish a workflow where you have certain naming conventions that you want to follow. And for example, you have a production process that naming convention keeps repeating. So with a plugin, what you can do is to kind of maybe automate the process where you have that nomenclature or the naming convention being every time implemented So that is the biggest advantage. So names that you put in the CAD comes as such in Simerics, so you don't need to do renaming and rearranging of the CAD in Simerics. The next question from Dingo is, what are the recommended aspects of consideration, fluid property geometry, for estimating the error range for running Simerics simulation? What were considered for the error bar estimate in the churning loss results? Let me share the slide. Slide 39 is what Dinghao is referring to. Yeah, so this error bar is based on how much, for us, I think in testing, it's like multiple tests they do and they have a variation. Because the spin loss, as we understanding, testing can also have a lot of variations. So, but for us, it's about like how much our power kind of oscillates. There is an error in terms of numerical accuracy, a mass error, but the mass error is for this type of simulation the order of like 0.5% or, compared to the total volume. So that's not significant. So this error bar that we show here is just the amount of dip and rise that the power has. As you go in higher speed, you'll see that the dip and rise is larger. So it goes from 1300 watts to maybe 600 watts, whereas the lower RPM, it's a little bit lesser. So we go from 100 to 200. So that's why I think we have this kind of bar, because we don't know the testing accuracy of capture of the data, probably in terms of amount of time or discrete points they have could be different compared to ours. So the next question is from David. How do you deal with the skewness of the cells? Could it be an issue if I want to study an oil jet hitting a rotating gear? Yes, skewness is not an issue. I would say we try to strive for orthogonality of the cells to the flow field as much as possible. But with hex mesh, you will have some regions where the flow is not orthogonal to the mesh, but still it deals with it quite reasonably well. We do have this upcoming study that we are doing with jet cooling of the gearbox. So we are hoping that we have some test data to kind of verify that, but that is still under the works, so I couldn't show it here. But we have done quite a few cases with that, and we have not found any issues with the fidelity of the results. It's just we need a little bit smaller time step because the jet velocities are typically quite large and the Courant number is larger. Yeah, so with that, I think we also have a feedback form. If you guys have any feedback on how to improve this, if you want us to bring more value with some other thoughts you have, please feel free to fill it up. With that, I really thank you all for your time today to spend with us. Thank Raghu and Dikshit as well for their contribution. Thank you all. We'll end the webinar now. Bye.
Thank you.
Thanks, Chirag.
Thank you. Thank you, Dikshit. Bye.